Everyone. Welcome in the fifth part of my course Microservices with Spring Boot and Spring Cloud. Today we'll talk about event-driven microservices with Spring Cloud Stream. This part is slightly different than 4 previous parts of my course since we are talking about new type of microservices-based architecture where such patterns like service discovery or client-side load balancing won't be very usable. That's why we need to change a little way of thinking about inter-service communication. In event-driven communication style, a consumer application may react on the event, but it doesn't have to do it. So our sender application may do not receive any response on the event from a receiver of a group of receivers. Currently, Spring Cloud Stream provides stable and opinionated support for two message brokers, Kafka and RabbitMQ. Of course, there are some other implementations available. Spring Cloud Stream application support consists of a middleware neutral core and a broker-specific binder implementation. Spring Cloud Stream provides a unified and elegant way of defining event-driven communication between microservices, no matter which message broker implementation we are using in our system. Thanks to that, we can just focus on defining integration patterns. In typical scenario, an application is sending events to a topic on message broker. On the other side, there are many applications that are listening for incoming events, and each of them may be run in multiple instances. So we may logically group them into the single consumer group to guarantee that only a single instance of each application is handling an incoming message. The latest version of Spring Cloud Stream has already introduced a functional programming model to define bindings, opposite to the previous version that were using an annotation-based support. In this tutorial, I'm showing the latest approach. So we are going to start with implementation of a simple publish-subscribe model. In the next step, we'll run Rabbit on Docker and use its web management console. I'm going to demonstrate how Spring Cloud Stream is realizing consumer group and partitioning concepts on RabbitMQ, since they are not supported there by default. These concepts are taken directly from Kafka. The last topic in the list is support for testing, which allows you to verify event-driven communication without connection to an external messaging system. As always, the source code with example applications is available on GitHub. So if you are interested in running them by yourself, check out the repository course Spring Microservices and go to event-driven directory. Okay, so let's start the implementation. Our sample system consists of 3 microservices. First of them, producer service, is responsible for sending events to message broker. Two another applications, consumer A and consumer B service, are listening for incoming events. We are starting our implementation from producer service. To enable Spring Cloud Stream for a Spring Boot application, we first need to include the right binder implementation dependency to our project. Because we are integrating with RabbitMQ, we need to include Spring Cloud Stream binder Rabbit. We don't have to include any other libraries with Spring Cloud Stream, since binder Rabbit library is referencing to all required libraries, including Spring Cloud Stream Core and, for example, Spring Boot Starter AMQP. After that, we may start an implementation. We are creating a class responsible for, which is an object representation of a JSON events sent by producer service. Its name is callMeEvent, and it consists of 2 fields, and ID field and message. After that, we may proceed to defining being responsible for producing events. As you probably know, Spring Cloud Stream has introduced a support for functional programming model. Within this support, we may use 3 types of beans responsible for message handling. One of them is a supplier bean. Supplier bean is generating a stream of events continuously and sending them to the message broker. Our supplier takes call me event as an argument, and it is incrementing its ID field before creating each single event. Of course, we need to annotate this method with bin, and it is also important to remember the name of this method, since Spring Cloud Stream is basing on this name by when generating a name of binding and a name of destination created on message broker. We already finished the first version of producer service. Now we may switch to consumer A service. We also need to include the binder Rabbit library there. And now we need to define a second bin responsible for message handling in Spring Cloud Stream, and this is consumer bin. Our application is just listening for the events. It doesn't send any response to the output, so we don't have to use a third type of bin, which name is function. We are just using consumer that takes call me event as an argument. We also need to create a class that is object representation of JSON message received by the consumer application. And we are just logging this object using SLF4j logger. It's also important to remember the name of method responsible for defining a bin. It is call me event consumer. In the next step, we are going to run a Docker container with RabbitMQ. We are using a version of image with management plugin. Thanks to that, we will be able to use RabbitMQ Web Management Console. The Web Management Console is exposed on port 15672. And we are also exposing a port for applications, and it is for TCP connections, and the number of port is 5672. After starting a container, we might take a look on the logs and check if everything has been successfully started. And you see it works fine. Rabbit Management plugin has been installed, and there are 2 defined ports exposed outside the container. Now we may switch to Rabbit Management Console. We are using guest credentials for logging. The most important things for us here is an ability to see the list of exchanges, the list of queues, and the list of channels. We are using a 3.8.3 version of RabbitMQ. After running a container with RabbitMQ, we may start both our applications. We are starting a producer service. You can see in the logs that it has been successfully established a connection with RabbitMQ. And it has been created a channel and a destination. The name of binding is call me event supplier out 0. It is generated as a concatenation of 3 parts. First of them, call me event supplier, is taken from a method that is registering a supplier bin, and out is defined for output type, and the 0 is an index of binding. And if you are not using multiple input and output support in Spring Cloud Stream, it is always equal to 0. As you see on RabbitMQ, we have a topic destination generated. After that, we can start a consumer A application. It has also successfully connected with RabbitMQ, and after that it has been generated a channel and a destination. The name is call me event consumer in 0. It's the same algorithm as over the supplier, but instead of out keyword we are using in which is dedicated for input type. Because we are using consumer, it is listening on input destination. And now we can verify it in Rabbit Management Console. You see that there are two topics created. It is not exactly what we wanted to achieve, because now the producer application is sending events to a different topic than consumer A service is listening on. So we need to overwrite the name of destination created for both bindings on the producer and consumer side. To do that, we need to use a property Spring Cloud Stream bindings with name of binding and destination field. Now a name of destination is call me events. We need them to set the same destination name on the consumer side. So we are using the same property, but we just need to change the name of binding. We can just copy it from the logs, and you see that it is also call me events. So now both applications will share the same topic on RabbitMQ. Now we can restart both these applications. Everything should work fine. You can verify it in the logs. You see that we still have a problem with deserialization from JSON into call me event object, but there is a problem with constructor that does not have default parameters. We'll change it later, but the messages are consumed by consumer application. We can verify it in RabbitMQ Management Console. You see that there is a 1 message per second sent by the producer, and 1 message per second is received by the consumer. So all the messages sent by the producer are consumed by consumer A application. And now we are going to refactor call me event class. We are setting a default parameters in constructor. We are adding a data keyword into the class to use default implementation of toString method. It is just using for logging. Of course, we need to restart our application. And now you see that it is receiving the events continuously sent by the producer. It is receiving all the events sent by this producer. In the next step, we are going to create the same implementation for consumer B service as for consumer A service. So we may just copy the code from consumer A service. We need to define a consumer bin and also override the name of destination basing on the generated binding name. You see, it has been changed, so now we are ready to start a third application, Consumer B service. The same as Consumer A, Consumer B is listening on call me events topic, and it receives all the events sent by producer application. So now there are two applications that listening for incoming events, and they are receiving the same events. We can verify it in the logs. We can also take a look on RabbitMQ Management Console. And you see that now sending rate in is 1 message per second, and the rate out is 2 messages per second, which means that there are 2 consumers on a single exchange. And the last thing in this part of our tutorial, we need to allow running multiple instances of the same application in IntelliJ. And now we are able to start a second instance of Consumer A service. And you see that it is also receiving all the events sent by producer applications. So now we've got 3 instances of applications, and all of them are receiving all the events sent by producer service. In some cases, it is not exactly what we expect from this model. So we want to guarantee that only a single instance of application is receiving the events. Consumer group mechanism may be enabled through configuration. So in fact, we don't have to do much to include it to a consumer application. But before enabling it for our application, I will show you how to use other interesting Spring Cloud features like event routing on the producer side or sending arbitrary data to an output on the consumer side. First, let's implement some changes on the producer side. We will increase the level of logging for Spring Boot AMQP library. As you probably know, RabbitMQ uses AMQP protocol in a communication layer. Thanks to that change, we will be able to see the detailed structure of messages sent to a message broker. In the next step, we are going to disable continuous stream of messages generated by a supplier. I leave a possibility of enabling that stream once again by declaring a configurable property callMeSupplierEnable. Now it is set to false. The property is injected into the application. We are changing the implementation of supplier method. If a value of callMeSupplierEnable is false, the supplier implementation is returning null object, what is the same as not to sending any message. Otherwise, our supplier is working the same as before the changes, so it is continuously sending messages once a second. Of course, we could just comment out a code to disable supplier bin, but the currently implemented solution is more elegant. Okay, let's consider why I decided to disable supplier mechanisms on demand. Now we will add a mechanism that allows to send a single event on request. Our producer service application will be exposing REST endpoint that triggers sending of an event to a message broker. In the first step, we are creating a REST controller available under path producer. It contains a single post endpoint with path parameter used for sending message to a broker. In that case, we are going to send a message from the external source that is not a binder like REST endpoint. You may use 2 different mechanisms. You can use a meter processor for reactive application and Stream Bridge for imperative programming. Stream Bridge bin is by default available for Spring Cloud Stream applications, so we just need to inject it to our controller class. After that, we can just call send method that takes 2 parameters, the name of binding and the object representing payload of sending message. We are also incrementing ID field of sending each new event. If you are using Stream Bridge in your application, you need to set property Spring Cloud Stream source using the name of your source. So in the preceding example, the name of the output binding will be still callMeEventSupplierOut0, which is consistent with the binding naming convention used by functions. After all currently described changes, we may start a producer service. We may verify in the logs that it is still using the same callMeEvents destinations, but unfortunately it doesn't expose REST endpoints over HTTP. That's why, because we didn't include Spring Boot Starter Web responsible for setting auto-configured embedded Tomcat for application. By default is on port 8080, so we should first include this dependency. After adding that starter, we may restart our application and call its REST endpoint responsible for sending event to a message broker on request. We are using producer context path and a path parameter with a message. Since it is returning true as a response, it means that the message has been successfully sent by stream bridge. Now we can switch to the application to see the detailed log with message body and other properties. Such an information is logged by Rabbit template bit. We may also verify it using Rabbit management console. You see that there are two messages sent by the producer. In the next step, we are running two instances of consumer A service. And now we may analyze what exactly is happening if we are sending new event to RabbitMQ. And as you see, the event has been sent by producer service and is being received by two active instances of consumer A service. It finally brings us to the issue with consumer grouping. If we want to guarantee that only a single instance of consumer A service is processing the request, we need to set property group on each binding using the name of group. In our case, the name of group is A. After this simple change, we may repeat our simple test with sending a single message by producer service. Now, such an event is processed only by a single instance of customer service. Let's clear the logs before test, and now we can call our test REST endpoint and verify logs. You see that only a second instance of consumer A service has received a message. We should also set the name of group for customer B service. In that case, this name is B. But before running this application, we are going to provide a little bit more advanced configuration than for the previous consumer. To do that, we are enabling event routing feature. Routing function will be bound to input destination, receiving all the messages, and to route them to other functions based on the provided expression. This expression should be set using Spring Cloud Function Routing Expression property. We are using Spring expression language to define a required routing instruction. Our expression is based on a header 2 process set on the event by the producer application. As a result, this expression should return the name of function used for handling event. We are defining two functions, process and fire forget. Now we may proceed to the implementation. We need to change a little current version of code. We are creating bins with the names corresponding to the names returned by the routing expression instead of a single default consumer bin. In fact, the only difference in the implementation is in the log. It's not all. We also need to change the configuration of target destination and consumer greens, since after enabling event routing feature, the name of binding has been automatically changed from call me event consumer to a function router. After that change, we may finally start consumer B service application. Now we are going to send test request. Because currently producer service does not set toProcess header on message, an incoming event is routed to the fire forget consumer. To test a scenario with toProcess header set, we are switching back again to the producer service implementation. I'm going to add there another REST endpoint, which is setting the header on outgoing message. To do that, we have to use method createMessage from message builder that allows to set a list of headers. The value of toProcess header is taken from a path variable. Now we have two REST endpoints exposed by this controller. We may call a new endpoint and set a toProcess header to true. Okay, now we are setting a list of headers. We are using a map. Of course, we are setting only a single toProcess header. We are taking a value of this parameter from path. Now we are restarting producer service application. We are clearing the logs once again. And now we can send a test request to the new endpoint with process and a value of toProcess parameter. In theory, everything should work fine, but unfortunately the header that has not been sent on the message by the producer service. I have been thinking much about it, and finally I figured out that it is a bug in Spring Cloud Stream library. You see that the implementation is provided, the headers are provided, so it has already been reported and fixed in the next version of Spring Cloud Stream. Currently it is fixed in a milestone version of next Spring Cloud Stream release train called IVLand. But in our case it does not work because we are basing on the latest stable version called Horsham. Fortunately, this bug doesn't apply to a supplier implementation. So now we'll enable our supplier. Before that, we need to change a little implementation of builder, of message builder, and we will use a message builder with payload method. We are calling a setHeader method on this builder, and we are changing a definition of our supplier to return not only the payload, to use not only the payload but the whole generic message with the headers. Now we are enabling this mechanism, supplier mechanism, in configuration properties. We can restart the application. You can take a look on the generated logs, and as you see, it has been set a header to process with the value true. And we can verify that this event has been properly routed on the consumer side, and you see that it calls a received process method instead of a fire forget method to process the event, so everything works fine. We can switch to RabbitMQ management console. You see that there is still a function router out, but it is not used in our case, and function router in zero binding has been mapped to call me events. You see that there are two consumers of that group, call me events A and call me events B, which have been logically related in the group A and group B, and there are two queues that are receiving this event. The next topic discussed in this part of my course is partitioning. Partitioning is a critical concept in stateful processing, where it is important to ensure that all related data is handled together. So thanks to partitioning, we may implement an algorithm responsible for distributing messages across multiple instances of applications in a determined way. To enable partitioning on the producer side, we need to set two properties related to a given binding. It is producer partition key expression, which in that case is the ID field of call me event, and a producer partition count with a number of partitions. This number should be the same as the number of running instances of application, since our partition is assigned to the selected instance of that application. Because we are planning to run two instances, we are setting such a value. To enable partitioning on the consumer side, we need to enable a single property on a given binding. The name of this property is partitioned. We also need to set a property Spring Cloud Stream instance count using a static number that represents a number of deployed instances of an application. While Kafka supports a more flexible way of partitioning configuration, Rabbit requires a static value, so we can scale up number of instances dynamically without changing these properties. We also need to set a property Spring Cloud Stream instance index for every single instance of application that uses a partitioning. It needs to be equal to 0 or 1 if we have two running instances. After starting both instances of a consumer A service, we can take a look on the logs. Now you see that this instance is receiving events with even numbers as the ID field. Now we can run the second instance, take a look on the logs from the second instance of consumer A service, and we may verify that the second instance will receive only events with odd numbers as a ID field of call me event. So let's do that. And now we see that it is 142, 144 for a first instance of consumer and service, and 151, 153 for the second instance of consumer service. Now we can take a look on the structure of exchanges created on RabbitMQ. There are two consumers listening for incoming events per a single consumer group. So if we have two different consumer groups defined there are 4 consumers in total. Within each group we have 2 different routing keys set for each target queue. And now we may also verify that there are 4 queues that are receiving incoming events. Now we are proceeding to the last topic in this part of my course, testing. Spring Cloud Stream provides an easy way of testing your microservices applications without need to connecting to external messaging system. Let's try it. We are starting our implementation of test method from removing existing Docker container with RabbitMQ since we do not need it anymore. In the first step, we need to include a required dependency with testing support from Spring Cloud Stream. We need to set a classifier test binder and a type test jar of 3.0 pre-release version of Spring Cloud Stream. Now we may proceed to the implementation of JUnit test class. We are creating a router function test class, and we are annotating it with well-known Spring Boot test annotation and passing there a single main application class. Now it is important to add an import annotation that includes test channel binder configuration to our test. Then we need to define two bins: input destination and output destination. Then we will use this bin for sending an input message and receiving an output message that has been sent by our application. Here is our test method. But before starting working on our test, we first need to perform a change in our existing class. So first we need to add a callMe response object, callMe response class that is assigned to the response message sent by our consuming application. Until now, we were not sent any messages to the output destination. Now we will change this behavior, so we will comment out the current version of process method, and we will change the consumer bin into the function bin. Function bin is able to send a message to the output destination. So now we are creating a method that is logging an incoming event, but also it is creating an callMe response basing on the ID from callMe event input and send it to the output queue. By returning the callMe response object from this function, we are just sending it to the output, and we are setting the same event that is inside callMe event, and we are registering a new method responsible for processing our input event. And now we are using send method from input destination to build a message, to build and send a message. We are using message builder, and it's with payload method. We are creating a callMe event object, and we are setting a header to process. It is important because we are testing a routing function in this test, so we need to set such a header for our application. As you see, we've got here a header expression. It is based on toProcess header. After sending a message, we may receive a response from output destination using its receive method. And now we are performing some assertions that response is not null and it has a body. Now we can convert response payload from byte to string. Of course, it is a JSON representation of objects, so we need to use an object mapper and deserialize this string JSON into the callMe response object. And after that, we also perform some verifications, like verification of an ID value and message value. And in fact, that's all what we have to do to create our sample test. So we may proceed to running it. Our application is starting. You see it in the logs. And now it is running the test. As you see, it has been successfully performed. See that the event has been consumed and everything works fine. That's all what I have planned to say about Spring Cloud Stream. Of course, that is a set of selected features of Spring Cloud Stream useful for building event-driven microservices architecture. For more details, you should refer to the Spring Cloud documentation. Thank you for watching this part of my course about microservices with Spring Boot and Spring Cloud. See you soon in the next part of my tutorial. This time we will talk about testing.